Wouter Janssen from the Cosys-Lab research group from the University of Antwerp in Belgium. And I am delighted to talk to you today to show our demonstration on mixed reality 3D in-air ultrasound applications as presented at the IEEE Sensors 2022 conference in Dallas. As the title explains, we will be using mixed reality, also called augmented reality, and we'll be using it within the context of ultrasound applications. When we think of sensors and ultrasound, we are of course talking about sonar, which most people know from how bats perform echolocation to sense the environment and find their next meal. Or how the parking sensor on your car is usually a simple sonar sensor that detects the distance to the surrounding area around the car. Or how submarines and other marine vessels use sonar to sense other vessels and the surrounding environment underwater. We at Cosys-Lab develop our own sonar sensors. We specialize in creating in-air sonar with dense microphone arrays that can create high-resolution 3D images of the surrounding area. As you can see, we make them in various sizes. And in this demonstration, we would like to show how our sensor uses the ultrasound spectrum and can serve various applications. In the first part of our demonstration, we would like to show our sensing technology when it's working in its passive mode. This means that we are not actively sending out an ultrasonic pulse from our emitter, but are only using our microphone array to listen for ultrasonic sound sources and localize them. This can be used for various applications, and today we want to show one of them. Because one primary source of ultrasonic sound are air leaks. While air leaks are not visible to the human eye, we can sometimes feel the air or hear it in the human hearing spectrum. But for this to work, we must get really close to the leak, and if it's very small, as they often are in industry, they become very difficult to locate and fix. And while one small air leak isn't a big problem, adding them all up is. It is said that all the air leaks in Europe alone cause enough lost energy of the magnitude of one nuclear power plant. Many companies are more than willing to fix these leaks, but the problem is not how to fix them, but how to find them. While there are solutions out there, these still require you to get close to the source of the leak and lack any form of automation. Furthermore, these solutions are very costly. In our interactive demonstration, we want to show how our sensor can detect even the smallest of leaks. We have mounted a 3D in-air sonar sensor with a circular microphone array on a mixed reality headset with built-in cameras. We will use this combination to show the user that puts on the headset how the human eye cannot see the leaks, but our sonar can. The demonstration includes a set of small pipes in which a low pressure of around 1.5 bars is actively going through. In certain places, very small punctures have been made of 0.3 millimeters. The goal of the interactive demonstration is that the user puts on the headset and finds, using our sonar sensor in the mixed reality configuration, these leaks. The headset displays the camera pass-through, on which, using augmented reality, the leak location is shown using a red circle when it is detected and located by our 3D sonar sensor. In the footage, we will switch between showing the person in the room as well as the view that the person sees within the mixed reality headset. As you can see in the video, the red circle shows up when the air leak is detected by the sonar sensor. The person can go and feel the air with their hand when they get close enough, but otherwise there is no way to detect with the human eye where the leak is located, especially from a distance. This mixed reality display is a great demonstration of what a sonar sensor can detect in the ultrasonic spectrum. For an industrial solution for air leak detection, we have developed a better system. When combining multiple 3D sonar sensors, a laser scanner and a set of cameras, we can provide an automated air leak detection system. Imagine the system being placed on a forklift that already drives through an industrial environment on a daily basis. Placing the system on top of it will create a huge dataset of these 3 sensor types during the day. At the end of the workday, this data can then be fused together into what you can see on the right. A top-down map of the environment created by the laser scanner, combined with the locations of the detected air leaks by the 3D sonar sensor in high accuracy. Combining this with an image of the camera showing exactly on the piping where the leak was located. This allows the leak to be easily located and fixed. In the second part of our demonstration, we would like to show our 3D sonar sensor when it is in its active mode, meaning that the emitter this time will be emitting an ultrasonic pulse. This pulse will be reflecting on the environment, which in return will be picked up by the microphone array again. Using our filtering techniques, we can construct an accurate and high-resolution 3D point cloud of the objects that it detects. Once again, we use the same environment and mixed reality headset, but this time no red circles are drawn, but a 3D point cloud is there instead, where the size of the points is indicating the reflection strength and the color the distance to the user. As you can see, when the person gets close to the poster boards or the walls, it is detected by the sonar sensor and displayed in the point cloud overlaid over the camera images. It becomes even more visible when turning off the camera pass-through of the mixed reality headset, so the user can only see the point cloud. In this view, the demonstration shows what it is like to only use the ultrasound information to sense the environment. As you can see, this data is very sparse, much sparser than, for example, a modern 3D laser scanner. But to give this sparsity some more perspective, our sensor is not developed to replace a laser scanner or camera. These types of sensors use the medium of light, and when the conditions deteriorate with fog, mist, rain or snow, these sensors become less reliable. Furthermore, in difficult environments where there's a lot of dust and dirt clogging up sensors using the medium of light will have difficulty to continue to operate safely and provide expected behavior for autonomous tasks such as mapping or navigation. Our sonar sensor, using ultrasound as its medium, does not have these issues and continues to operate normally under rough conditions due to the different wavelength it operates at. It can be an excellent sensor for agriculture, mining, heavy industry and others. In other publications and demonstrations in the past, we have shown our 3D sonar sensor to be capable of mapping entire indoor and outdoor environments and localizing itself within it, or doing real-time autonomous navigation while avoiding hitting objects and staying on course. Using a sonar sensor such as ours, either as standalone or in a sensor fusion model with other sensor modalities, can provide a user with a safe, reliable, and accurate system. To finalize the demonstration, we would like to provide some more details about our sensor. We are currently, and have in the past, worked together with biologists to better understand the echolocation performed by bats and how they interact with the environment and other species. We can learn from them and try to adapt their methods into our bio-inspired sensor and application design. We continue to do so while developing our state-of-the-art sensor and collaborate with industry partners. As shown in the previous sections, our sensor contains a single emitter and a dense microphone array. By using a dense microphone array, you can have unambiguous target localizations at the price of a lower resolution. To counter this, one could choose for a larger aperture to get a higher resolution result, but this would create high ambiguities for target localization. We mitigate the ambiguity by using randomized array design, for example by using a genetic algorithm to generate the ideal microphone positions. By using low-cost MEMS microphones, the production cost remains low. To go from the microphone signals to the high-resolution 3D images, we have a signal processing pipeline that works as shown here. We first look for the original pulse we use in the active mode using a matched filter. Afterwards, we use beamforming to steer the microphone array like an acoustic lens in the directions of interest. Some additional filtering like an envelope detector is used for cleaning up the 3D image. We have developed accelerated software on GPUs to make the signal processing possible in real time. This provides us with results that can be achieved up to 20 times faster than when calculated with our previous method on a CPU. Therefore, in our main implementation of the sensor, we have an integrated NVIDIA Jetson as a GPU platform to do the real-time processing on board. This is the sensor seen on the left. But we also have developed them in other shapes and sizes, from smaller to large, from 3 microphones to over 1024. Our sensors can work passively and actively. Furthermore, it can see up to 50 meters and passively even double that distance. With an accuracy of 1 degree and 1 millimeter in angular and range respectively, and a 180 degree field of view that can see the entire frontal hemisphere of the sensor. Furthermore, we can operate it at the measurement rate of 15 Hz. As we fully develop the hardware and software within our research lab, we can create custom designs as the ones used for this demonstration, mounted on the mixed reality headset. By integrating our sensor with other sensor modalities, we can create sensor fusion models with, for example, high-speed cameras. or multiple sensors can be integrated together and use hardware synchronization. Our sensor technology is multifaceted and can serve many applications and can be a solution to various problems. Thank you for watching and listening. We hope you found our demonstration interesting, and if you have a question or would like to talk to us, don't hesitate to contact us.